So yeah, thanks for the introduction and for the invitation. So I hope to explain all these words to you if you're not already familiar with them. And yeah, I'll just start by saying this is joint work with Jorge Garza Vargas, Archie Kulkarni, Shatuki Mukherjee, and Nikhil Srivastaval from UC Berkeley at the time of writing. So the problem that we'll be talking about solving is the problem of approximating the eigenvalues of an arbitrary complex n by n matrix. Very important problem, as you all know. And it's important to distinguish between two different ways or two different meanings of approximation here. So one is the notion of forward approximation, where I give you a matrix, I give you some accuracy parameter delta, and I want you to find numbers that are close to the actual eigenvalues of the matrix, the spectrum. The other notion of approximation is backward approximation, which is a little bit relaxed. It just says, I want you to find the eigenvalues of a matrix close to the matrix I'm interested in, again, parameterized by this accuracy. And so today we're going to be talking about backward approximation. And on the next slide, I hope to explain to you why that is the kind of necessary state of affairs here. But just before we go to that, there's a couple of different computational settings in which you could be interested in this. So one is exact arithmetic, where you imagine some idealized computer that can store numbers, real numbers, that is, exactly. And so the cost of the algorithm, maybe you could measure as the number of arithmetic operations. Not very realistic, but useful for analyzing things before you can get to the real deal, which is, of course, floating point arithmetic, which our computers actually use, where you store numbers up to some finite precision using around that many bits, and every arithmetic operation you do is approximate and has relative error controlled by this machine precision U. And then the cost of the algorithm, of course, is not just the number of arithmetic operations, but it also depends on the precision, right? If you're using more bits of precision, more expensive. So you can measure it as the number of bit operations, the number of pairs of bits you actually need to manipulate. And so the work I'm going to be talking about today ultimately is about solving this backward approximation problem in floating point arithmetic. But for most of today, we're going to be talking about exact arithmetic, because that's where actually a lot of the meat of the particular algorithm that I'll be talking about lies. And then I'll talk at the very end about how you can move from exact arithmetic to floating point arithmetic. And so the star of the show today is the shifted QR algorithm. How many of you are familiar with this algorithm? You can raise your hands. Great. Okay, so a few. This is one of the oldest, most well-studied, most widely implemented algorithms for solving the approximate eigenproblem. It's used in basically every platform for numerical linear algebra. If you call eig on your computer in MATLAB, this is what runs. And as we all know, because we do this a lot in our jobs as mathematicians, this algorithm works very well in practice, right? It's fast and it's accurate, and that's terrific. But there is, I would say, a really large gap in theory about this algorithm. And by theory, I mean like theoretical computer science results that say, if you run this algorithm on a computer using this many bits of precision, it'll run fast and is guaranteed to give you something accurate. And so the purpose of this work is not to propose new implementations for this algorithm, which is already very good, but rather to understand why it's doing what it does, to try to marry theoretical computer science, numerical linear algebra. Okay, great. Let's begin. So why is it that this is a hard problem or an interesting problem? The thing that makes this problem hard in the case of non-normal matrices is that they can be spectrally unstable, meaning you can perturb them a small amount and their eigenvalues move a lot. And going back to these notions of approximation, this is why backward approximation is the name of the game here, right? Because if small perturbations of the matrix can produce macroscopic, really large changes in the eigenvalues, then as your algorithm is running in floating point arithmetic, you're doing lots of rounding, you're making small perturbations to the matrix, and the eigenvalues potentially could go all over the place. So let's see an example of this. So let's look at a matrix which has ones on its superdiagonal, epsilon in the lower left corner for some small epsilon, and is zeros everywhere else. And you can calculate by hand that the characteristic polynomial of this matrix is just z to the n minus epsilon. meaning that its eigenvalues are the nth roots of epsilon. So to put that another way, an order epsilon perturbation, very small perturbation, from J0 to J epsilon moves the eigenvalues by epsilon to the 1 over n, which is a lot, right? And so this means that you would, if you wanted to solve the forward error version of the eigenproblem on this matrix, you would need to use a ton of precision. It'd be very expensive. So there's some ways to quantify this behavior, which I'll return to a couple times in the talk. So one is this eigenvector condition number, kappa v, which measures the best condition basis of eigenvectors for a matrix, condition number of that. The other one is the eigenvalue gap. And you can check that as epsilon goes to 0, both of these measures of nonnormality or spectral instability or whatever are blowing up or going to 0, as the case may be. Any questions about this? Okay, good. So given that there are matrices like this one, which are spectrally unstable, which have arbitrarily ill-conditioned eigenvectors and arbitrarily small gaps, what are we to do in the world? Well, the line of work that I'm talking about takes a particular kind of smoothed analysis approach, where, although these matrices exist, they are rare in kind of a quantifiable sense. So let's see results to that effect. So if A is any matrix, could be the matrix from the previous slide, and G is a normalized complex Geneva matrix. In other words, it has independent complex Gaussian entries, and delta is some small parameter, then with fairly large probability, the eigenvector condition number of this matrix is pretty well controlled. It's polynomial in n over delta. And its eigenvalue gap is also well controlled. It's the inverse of that. And moreover, this matrix delta G is somewhat small. And so you can think of this as saying, okay, I'm interested in solving the eigenproblem on some matrix, could be the matrix from the previous slide. So what am I going to do? Well, first I'm going to add this small perturbation, say, A plus delta over 8 times G or something. And that's going to take me to a matrix, excuse me, with well-conditioned eigenvectors and with large gaps. And on that matrix, then I'm going to run some algorithm, and I'm going to use those features, that well-conditionedness, to analyze the algorithm. And the point is that since we're doing backward approximation, right, since our goal is to find the eigenvalues of a matrix close to the matrix we started with, it's totally fine to use some of that budget of backward error to pass to a well-conditioned matrix on which the algorithm might run better. Okay, so this is the kind of meta approach here. And today, what I want to talk about is a particular algorithm, the shifted QR algorithm, and understanding it on matrices which are well-conditioned in this sense, right? So we're going to assume before the talk started, we already took our matrix and we conditioned it in this way. And now we're going to think about the algorithm of interest on a well-conditioned matrix. Sound good? Great. So now we have to talk about the QR algorithm. Only a few hands went up, so I'm going to spend a while talking about how this algorithm works so that we can say what exactly we did. So for those of you who already know all about this, you can put your feet up and hang out and daydream about lunch, whatever you'd like to do. So to get started, thanks to Alan for prefacing this factorization. This is something useful you can do with the QR factorization. Remember that if I have any matrix, I can write it as Q times R, where Q is unitary and R is upper triangular with non-negative diagonal, say, and that non-negativity makes this a unique factorization. Okay, so this is nice. And here's something you can do with this factorization. Let's say I start with a matrix, and to produce, I'm going to do a sequence of iterations. And to produce each iterate from the previous one, I'm first going to compute the QR decomposition, and then I'm going to reverse the order of Q and R. Okay, so I'm going to do this for a while, and equivalently, since Q is unitary, this just means I'm going to conjugate each iterate by the Q from the QR factorization to produce the next iterate. And then we're going to do this and see what happens. So it's not clear immediately when you see this definition what is going on or why you might do this. And here's a little lemma that ties this back to some maybe more understandable operations that you might do on a matrix to try to pick out some particular eigenvalue. So the lemma says for each of k equals 1 to n, I hope that I stated this correctly in terms of the rows and columns. You can scold me if not. So the deal is that if I accumulate all these Q matrices that I've used in the course of the algorithm, and I look at the first k columns of that product, those columns for each k span the first k columns of a power of a. And similarly, the final k columns span some rows of the inverse powers of a. And so, in other words, if you set k equals 1, for instance, this Q matrix is encoding like power iteration on your matrix A, starting from the vector E1. And it's also encoding inverse iteration on the matrix A, starting at the vector En. On the left, that is. So this isn't going to be relevant for the rest of the talk, but just to say that QR iteration actually is doing something interesting, and it's kind of encoding a lot of other things that you already know about, like power and inverse iteration. So using some arguments kind of like this, you can show that if you do this iteration, you end up, at least generically, converging to an upper triangular matrix, actually the Schur factorization, or the Schur form of A, and that the rate depends on the ratios between the moduli of eigenvalues of your matrix. Okay. So this is kind of nice. This does give a way to produce the eigenvalues of an arbitrary matrix. But there's a couple of issues, practically speaking. The issues are that, well, for starters, this is expensive, right? Doing QR decomposition and then multiplying the two matrices. Sorry about the, takes a long time. So each iteration is expensive, and also this convergence rate can be arbitrarily slow, right? This is just no good if you have a unitary matrix or something. What are you going to do? All right. So the modern form of the QR algorithm has a couple of innovations that deal with these issues. So one is the use of Hessenberg matrices. So a Hessenberg matrix is a matrix that looks like this. It's a triangular matrix plus a little extra. And so let's just assume that the subdiagonal is non-negative, just to keep things simple. Okay, so why am I telling you this? Well, one fact is that if I start with any matrix, I can bring it to Hessenberg form. So I can go to a unitarily equivalent Hessenberg matrix in not too many arithmetic operations. So how do I do this? Well, I have some full matrix here. By operating just on these rows and these columns, I can zero out a row. And then I can do this again repeatedly. And I end up with a Hessenberg matrix. And you can actually do this quite cheaply because you just have to apply like a reflection. Okay, so no need to work with arbitrary matrices. At the cost of n cubed operations, I can just work with Hessenberg matrices. Sounds good. The other nice thing about Hessenberg matrices is that actually you can do a iterative, like an iteration of the QR iteration quite cheaply. So how do you do that? Well, it's really easy to take a Hessenberg matrix to triangular form, because again, just by using a little reflection or rotation on the top two rows, I can zero out an entry, I can zero out another entry, do this for a while, I get the triangular form. And then I can apply again all these orthogonal little flips again on the right, and I'll get to another Hessenberg matrix. And that's exactly conjugating by the unitary matrix in the QR decomposition. Okay, so this can be done quite fast, again, because we just have to operate on two rows at a time. So those are two nice things about Hessenberg matrices in the context of this algorithm. There's another nice thing, which is that it actually eases convergence in a particular way. So let's say that I start with the Hessenberg matrix and I start running the QR iteration. And we find that some subdiagonal entry is really small. So just to have some notation, let's say it's omega decoupled if some entry is less than omega times the operator norm of A. Well, if you get to this point, you can actually just zero out that entry. And then the resulting matrix is block upper triangular. And each of the blocks is itself a Hessenberg matrix. And so you might as well just keep doing the QR iteration separately on these two blocks. Okay, so this is a nice feature of these matrices as well. And so this process of making an entry small is called decoupling. This process of passing to two smaller matrices is called deflation. So these are things that are also used in this algorithm. Okay, so this all is helping somewhat with the two issues I mentioned on the previous slide. The remaining issue is that convergence can be slow, right? None of these things is changing the ratios between the moduli of different eigenvalues. So we need some way to do that. And so this is done with this notion of shifting. So you know, if you want to change the ratios of moduli of eigenvalues, one thing you can do is just translate the matrix, right? That'll translate the spectrum. It'll take a unitary matrix to something with slightly improved ratios between its eigenvalue moduli. The problem is that you don't actually know what the eigenvalues are, so you can't ahead of time figure out a magical shift that will fix this issue. And so the idea of the modern QR algorithm is that you adaptively choose these shifts. You actually choose some polynomial, you apply it to your matrix, you hope that the polynomial is making the ratios between eigenvalue moduli better. You do a QR step, and then you do it again. And so again, to have some notation here, let's say we have some function, some shifting strategy, which assigns to each Hessenberg matrix a polynomial. And then you do the following iteration. So you take the matrix to Hessenberg form. First, you compute this polynomial from some iterate. Then you compute the QR decomposition of the polynomial applied to your current iterate. And then you use the Q that you found and apply that to your current iterate to get the next one. Okay. So, if this polynomial were the same every time, this would just be like a single global translation you would apply to your matrix, and then you would just be running the naive QR iteration. But this way you kind of have some adaptivity. You can change the polynomial set somehow. And so the problem here is what shifting strategy should you use? What's a way of assigning polynomials to Hessenberg matrices that actually makes this iteration converge rapidly? I'll pause here before we start to answer this question and see if there's any questions with what I've just told you about. So, I mean, there needs to be some global rule for choosing the polynomial. It can depend on the matrix, though. It can depend on the current iteration. Questions? Okay. So let's talk about some prior work. All these are results in exact arithmetic, I should say. So for this should be Hermitian or symmetric tridiagonal matrices. There is a shifting strategy which gives you global linear convergence. It's called the Wilkinson shift. And how it works is you look at the two eigenvalues of the lower right corner of your matrix, and you choose one of them, whichever one is closer to the lower right entry, like the NN coordinate, and then you use that as your shift. Okay, so this looks perhaps a little unmotivated, and indeed, I felt that way for a long time. It turns out that this is the correct thing to do. You can get very fast convergence this way. And later on, we'll see kind of a souped up version of this, which still uses the eigenvalues of some lower right-hand block of the matrix. Yeah, go for it. Sorry? Yeah, right. So I missed a word on the symmetric or Hermitian tridiagonal matrices. Yeah. Okay, there's also some results for unitary Hessenberg matrices where there's a shifting strategy which gives you global linear convergence, but the bound on the rate is not so easy to use. And other than this, there's really not a lot of results of this form, which say here's a shifting strategy, it works globally, end of story. And especially not for some broad class of non-normal or non-Hermitian matrices. So to state the result that I'm going to tell you a bit about, we have to go to this notion of Ritz values of a matrix. So these are just the eigenvalues of the lower right corner of H, kind of like we used up here. And here's the theorem that we showed in some of this work. The theorem says, okay, if you look at Hessenberg matrices with bounded eigenvector condition number, so well-conditioned, spectrally stable Hessenberg matrices, then there's a shifting strategy. In fact, there's a family of shifting strategies parameterized by some number k, same k is right there. And it has these two properties. One, it decouples quickly. So this means that it drives some entry below omega in like log of 1 over omega entries, iterations rather. No matter what matrix, what Hessenberg matrix in this set you use or start with. And furthermore, it's fairly cheap to apply each iteration and to compute the shifting polynomial. So yeah, exactly. So I mentioned this briefly on the previous slide, but omega decoupled means that one of the subdiagonal entries is smaller than omega. So this is the time necessary to drive one entry smaller than omega. And then once you do that, you do this deflation thing that I talked about before. Okay. So this is kind of a mouthful of an expression, but this thing is like order 1 if you set k to depend on the eigenvector condition number. And it only depends very mildly on it, right? Yeah, go for it. So yes, I was being a little sketchy with this. So it is a randomized algorithm. You can kind of set it up in different ways, but yeah. Yeah, I mean, this cost is like the cost of computing the shifting polynomial and applying the iteration. So I'll tell you a little bit about how the shifting strategy works. Okay, good. So just as a warm-up that'll take probably the rest of the talk, let's see how this works for normal Hessenberg matrices, which have a lot of extra structure. So here's the idea. So we want to decouple. So our goal is to decouple the matrix by making one of these two entries small. Okay. And we're going to focus on these entries just for kind of convenience. And the strategy is going to be to use a shift like the Wilkinson shift that I mentioned before, that is some function of the eigenvalues of this lower right-hand block. Okay. Good. So to measure decoupling, it's really useful to have this kind of potential function that you use as you're doing the iteration to track how well you're doing. And instead of looking at like the max of these two things, which is the thing we're actually interested in, we're going to use the geometric mean of them, which turns out to have a more rich connection to the structure of the matrix. Okay, so as long as we can drive this down below omega, say, then the matrix will be decoupled. Okay, and the reason why this potential is interesting is because, as I was saying, it kind of relates back to the structure of the matrix. So in particular, there's this variational formula for it that ties it to these Ritz values, to the eigenvalues of the lower right-hand 2x2 corner of the matrix. So here's the formula that does that. So this potential, this geometric mean of those two entries, is actually equal to the norm of the last row when you apply this characteristic polynomial of the lower right-hand corner of the matrix to the big matrix. And in fact, this is the smallest this norm can be over all monic quadratic polynomials that you could apply to the matrix. Okay, and both of these facts will be kind of useful. Is the statement of this clear? Might seem a little unmotivated. I wish we had more time together to talk about why this is true. Okay, good. So this, the virtue of normal Hessenberg matrices here is that quantities like this row norm have another interpretation as well. So let's let f be some function on the eigenvalues of the matrix, just some rational function, say. And since the matrix is normal, you can write it as UD U star, where U is unitary. And so then if you start to compute these row norms, like we had on the previous slide, if you expand this out, let's look at the square instead of just the norm, you'll find that you can write this as this sum, where the sum is over the function applied to the eigenvalues, weighted by the entries of the last row of the matrix. And the point is that this you can think of as an expectation, right? This last row of the matrix has norm 1. And so this is the expectation of the square of this function with respect to a random variable, which I'll call ZH, which is supported on the eigenvalues, and the probability that it is lambda I is just this thing here, right? So this is not a deep statement. It just is a different way of thinking about things. And the support of this random variable is the eigenvalues, and if the support of this random variable were to be concentrated on a single eigenvalue, that would mean that that En is actually an eigenvector for that eigenvalue, right? Would just be saying that you can kind of take a look at the matrix U there. Okay, not so important, but just to say this thing is kind of encoding some structure of the matrix. Okay, so the final feature that we need here is that we need to understand how the potential, this geometric mean of the bottom two right-hand entries, changes when you apply a QR step using some shifting polynomial p. Right, so remember that this means you take h, you compute p of h, you compute its QR decomposition, and then you conjugate h by the q that you got. Okay? And what you'll find if you do a little calculation is that the potential of the outcome of this, you can bound in terms of one of these row norm like quantities. You know, that depends on this polynomial p that you use to shift. Okay, and you know, similarly by this kind of functional calculus thing, you can write this as this expectation of this random variable. Cool. So here is the basic part of this shifting strategy. So you look at these two Ritz values, these two roots of the characteristic polynomial of the lower right-hand corner of the matrix, and you choose the root that maximizes this quantity. And this will be relevant on the next slide. So just kind of file it away. So you choose the root that maximizes this, and then you use this quadratic shift using that root. Okay, so that's the shifting strategy. And it turns out that this shift monotonically decreases the potential. So let's see why that is. So again, let's say that we go from h to h hat using a QR step with this shift. So using this one step bound from the previous slide, you can control the potential at the next step using this inverse moment of this random variable ZH that we defined. You can then apply Jensen's inequality, and using the definition of the root that we chose. Remember, we chose this root to be the one that maximized this quantity, this expectation over the two roots. And so now this is definitely bigger than the average. And applying the AMGM, because this is all going on inside this expectation. This is why we defined this whole random variable in the first place, is so we can have an expectation, have linearity, and do stuff like this. Applying AMGM, you get to bound this by the characteristic polynomial of this expectation of the inverse characteristic polynomial of the lower right-hand corner of the matrix. And so then you can apply Jensen's inequality another time. And then the point is that now we had this variational formula for the potential of the current iterate in terms of exactly this expectation, right? So this was the purpose of doing all these steps. So this gives you that the potential is monotonically decreasing. So just a few different small facts that you assemble together here, and then one useful choice of like shifting polynomial. Okay, so this gives you monotonic decrease, but you know, there's no bound on the rate here, right? It could be that these things are equal, that the potential actually stays the same. And the important thing here is that if this happens, you get to learn a lot of information about the structure of the matrix. And in particular, you learn some things about where the eigenvalues are. So remember this, this ZH here is supported on the eigenvalues. And so if this potential equals that potential, then all these inequalities are equalities, meaning that every application of Jensen's inequality here is tight. There's an equality, which means that this distance, the distance between ZH, which is supported on the eigenvalues, and your root, R star, is constant. In other words, that the eigenvalues of the matrix are on a circle. And similarly, if you only had, if you didn't make very much progress, if you didn't have equalities here, but this was only a little bit smaller than this, then this picture would look almost the same, except for there would be a little annulus instead of a disk, and all the eigenvalues would be in the annulus. And so this is the ingredient that gives us the second part of the shifting strategy, right? So the first part of the shifting strategy is you try out shifting using this polynomial here. And if it didn't work, then you learn something about the structure of the spectrum of the matrix. And that allows you to choose a kind of exceptional shift. In other words, you're going to search over this circle or over this small annulus, and you can basically be sure that you'll find something close to one of the eigenvalues. And it turns out that once you do, that gives you a good shift, and you do get a good decrease in the potential. So that the big picture here is you choose some shifting strategy, you understand what happens when the potential doesn't decrease too much, and then that allows you to choose kind of an exceptional case shift that does give you a decrease in the potential. It's the high level. All right, so this was also normal matrices. There's some more stuff that you need for non-normal matrices, and even more stuff that you need to do this all in finite precision arithmetic. So let's very quickly talk about that. So the main thing you lose when you go away from normal Hessenberg matrices is you lose this functional calculus, because you no longer have unitary diagonalizability, right? But it turns out you can still define something like the random variable ZH that we had in the previous section by looking at like the entries of the last row of the eigenvector matrix. And it turns out you get kind of an approximate functional calculus if you do that. So it allows you to approximately relate these row norm like quantities that are coming up all over the place with expectations with respect to this random variable. And the thing you lose in this approximation is the eigenvector condition number of the matrix. So if this is pretty well controlled, then this approximation is pretty good, and you can kind of get something going. So there's some other ingredients you need too. In order to compensate for this like only having an approximate functional calculus, so what this does is on the previous slide, you'll only have like approximate monotonicity, but there's going to be factors of the eigenvector condition number all over the place here. And so to deal with that, you have to take very high degree shifts instead of just using, sorry, I'm flashing all over the place here. Instead of just using a quadratic polynomial, you have to use a much higher degree polynomial that like smooths out this, this eigenvector condition number issue. This will give you almost monotonicity of the potential, and then still, if you don't make a lot of progress in a single step, you still get that the spectrum has support on a small disk around around your shift, and you can do the same sort of exceptional shifting as we were doing before. Okay, so there's yet more problems when you go to finite precision arithmetic, right? All of these things are happening only approximately. And so you need to do some more stuff to fix that. So what you want, and another issue just by the way, is that once you move to higher degree Ritz values, right? The shift in the normal case was a function of the eigenvalues of a 2x2 corner of a matrix, which are things you can calculate exactly because they're just the roots of a quadratic polynomial. But once you get to higher degree shifts using higher order Ritz values, those are themselves the eigenvalues of a matrix. And so you need some way of approximating those, which is the whole problem that we're trying to solve in the first place. Okay, so you do this by using some additional precision to compute these Ritz values. We can talk about it after the break, whatever. There's another issue, which is that each QR step you do is unstable in a certain sense. And so you have to deal with that as well. And so maybe I won't even kind of try too hard to go into that since we're running up against time. But this is I hope at least will allow you to approach this sequence of 3 somewhat long papers with a little more framework for understanding what's going on. And I'm happy to talk during lunch and at other times about all of the work. So thanks for your attention.